Hey everyone, Mr. Fritz here. In this series of videos, we are going to talk about binomial. So why don't we dive right into it? Well, first let's recall Pascal's triangle. This is an activity we did in class, and we had 3 sheets of paper that all kind of revolved around this triangle. Let's kind of recall how that triangle looked. At the top of our triangle, we had a 1. We'd call this the 0th row. And then beneath that we had another 1 and another 1. This would be the first row. And then what we did is we created subsequent rows by adding the 2 rows above it to give us whatever the number was below it. And then we kind of added 1s on either side. And in one of those sheets we kind of envisioned zeros kind of spreading out in either direction on the sides with all these things. But we don't need to really envision that. We can just always put a 1 to start out each of one of these rows, and then we can add the 2 numbers above it to get the next number. So 2 plus 1 is 3, and then another row here. So this is the second row, the third row. Let's go down to the 6th row. So another 1, then a 4, then a 6, then a 4, then a 1, then a 1, then a 5, then a 10, then a 10, then a 5, then a 1, and then finally a 1 and a 6 and a 15 and a 20 and a 15 and a 6 and a 1. And we can find all kinds of cool patterns with this. If we were to take a look at the diagonal, for example, we see all the natural numbers, all the counting numbers, 1, 2, 3, 4, 5, 6. If we were to take a look at another diagonal, 1, 3, 6, 10, 15, we might see some sort of quadratic relationships. And there's all kinds of cool patterns that exist within the Pascal's triangle, but what we want to talk about in this video is how they relate to binomial expansion. So let's take that same triangle and let's kind of write this with our binomial expansion. That second sheet that I had you work on was how to expand the binomial x plus y, or we could say a plus b, to some power, to some n power. And if we are expanding a plus b to some n power, if n is equal to 0, it's equal to just 1. If it's equal to 1, then it's 1x plus 1y, or 1a plus 1b. And then you kind of follow this out throughout. Now the key thing to focus in on here is that all of these coefficients are whatever the Pascal's triangle row has in store. So the third row would correspond with x plus y, or a plus b, to the third power. So this is really helpful to us when we want to expand these binomials. And so x and y, or a and b, can be anything. And what we're going to do in this video is we're going to figure out how to use these coefficients and these patterns to help us to expand these binomials. So some things to take note on. When we expand the binomial a plus b to the n power, we need to keep in mind that n is a natural number. That's what this means. It means n is an element. It's an epsilon element of the natural numbers. Natural numbers are counting numbers, and sometimes we include 0 in that. So 0, 1, 2, 3, 4, 5, 6, 7, whole numbers. So as long as we follow this restriction, that this power is a whole number, then when we can look, as we look from left to right across the expansion, the powers of A decrease by 1, while the powers of B increase by 1. So if you look at, for example, the 5th row here, where we used x and y, the highest power of x was 5, and then we have x to the 4th power, then an x to the 3rd power, then an x to the 2nd, x to the 1st, and then this would kind of be an x to the 0 power, while we see that the y's all increase by 1 exponent. So there's that relationship going on. Also, the sum of those powers of a and b is always equal to whatever that n power is. Again, if we look at the example for Pascal's triangle up above, if I look at the 4th row, all of the powers, the exponents, sum to 4. And I know that we don't have an exponent here, but there's an implied first power there. So this all is also equal to the sum of these powers are all whatever this exponent is, and corresponding to the row of Pascal's triangle. Another thing to keep in mind is the number of terms in expansion is n plus 1. So that's really helpful, because if we have a binomial expansion to the 5th power, we should expect to have 6 terms. If we have a binomial expansion to the 3rd power, we should expect 4 terms, and so on and so forth. So that kind of helps us to keep in mind, if we know the number of terms, we are less likely to accidentally forget one. Also, the coefficients of the terms are row n in Pascal's triangle. That's kind of what we've been developing so far. So let's put this into practice. We can now expand any binomial because we can just kind of use a and b as placeholders and use them to formulate the expansions of all kinds of things. In this example, I want to expand this binomial 2x plus 3 to the third power using this binomial expansion as given by the coefficients in our Pascal triangle. So this is the third row, and it's given as 1, 3, 3, 1. So these are the coefficients in my binomial expansion. So basically what I need to do here is it's a little bit more complex because I don't have just a plus b like I do in the original expansion, but I have this 2x plus 3. Really, it's not all that much different if I consider this one whole thing as my a value. This 2x is just like my a. And then I could say that the plus 3, this is kind of like my b value, b equals 3. So I can use this, I can still use this general expansion for the binomial to the third power, and I'm just basically going to substitute in wherever I see an a 2x, and wherever I see a b, a 3. So why don't we write what this would look like with the coefficients first, and I'll just kind of leave some blank spaces for my a's and my b's. So this 2x plus 3 to the third power is going to equal 1 times a cubed plus 3 times a squared times b plus 3 times a times b squared plus b cubed. And now what I'll do is I'll just fill in wherever I see an a, I'll throw in my 2x's. So this is 2x here, this is a 2x here, this is a 2x here, and then for my b's I'll throw in a 3. So this is a 3 here, a 3 here, and a 3 here. So I'm just substituting into my general expansion of a plus b to the third power. I'm just substituting in whatever I have for my a and whatever I have for my b, depending on what this original binomial is for this problem. So now we're just going to kind of simplify and figure out what this is equal to. So this is 2x cubed, so that's going to be equal to 8x cubed, since that's 2x times 2x times 2x. Maybe we'll take this a couple steps out for this one. This is going to be 3 times 4x squared times 3. This will be plus 3 times 2x times 9. And this will be plus 27. Let's take it one more step and say this is 8x cubed plus this is 3 times 3, that's 9, times 4 is 36, so 36x squared, plus 3 times 2 is 6, times 9 is 54, so that's 54x, and then plus 27. So this is the expansion for this 2x plus 3 cubed. And this might seem like it's not really saving us a whole lot of time. We could have just taken the long end of it and multiplied it out. But this tactic of using this general expansion is going to help us a lot moving forward to higher powers. So why don't you try this example here. Pause the video, give this one a shot, use that general expansion, substitute your a's and your b's, and see how it goes. And so here is my solution for this problem here. Check it out. Hopefully it went okay.